FET biasing. Let's go to fourth point, that is called AC load line. AC load line. For example, FET here, supply RD, RS, CS. When for AC, CS is short circuit. For DC, CS is open circuit. When CS is short circuit, RS is 0. Here RS is not 0. Therefore, DC load line will have DC slope minus 1 by RD plus RS. AC load line will have AC slope simply RD. What happened RS? RS is missing because 0. So these are the two slopes. So if I have to sketch them, VDS, ID, VGS minus 1, VGS 0, VDD, VDD by RD, RS. Suppose if I take Q point here and AC slope will pass through this one. This is AC load, DC load line with the DC slope RD plus RS. AC slope 1 by RD. Now what is Q point? Therefore, Q point is intersection of AC load line and DC load line. Q point is intersection of AC load line and DC load line. They only have different slopes. And because of this circuit, this is VDS, ID. Fifth point, calculation of Q point. How to calculate? Step 1. Apply input KVL and obtain relation between VGS and ID. So when you apply input KVL, you will get an equation between VGS and ID. Then substitute in this equation VI equation. What are the VI equations you have? For JFET, ID is IDSS into 1 minus VGS by VP square. Enhancement MOSFET, ID is K into VGS minus VT whole square. Depletion MOSFET, ID is, we can, for D mass, we can say K into VGS minus VP square, or we can also say 1 minus VGS by VP whole square. So, depending upon the FET, we are going to use this equation. Because as you know, there are three FETs. JFET is there, enhancement MOSFET is there, depletion MOSFET is there. And what is the purpose here? And calculate VGS. Definitely you will get two values. Why two values? Because this is quadratic equation. Because of quadratic equation, you can have two values. Then step 3 is choosing VGS. How to choose? See, for example, JFET. Please remember, we are talking everything about N channel. For example, when you think about N channel, if it is a JFET, you will have two values, positive and negative. Take negative. If both are negative, take whichever is less than VP. Less than VP. If it is enhancement MOSFET, take positive and negative comes, take positive. If both positive, choose anything greater than VT. VT. If it is D MOSFET, UVGS will have positive and negative. Both are available because this is for enhancement mode, this is for depletion mode. You can use both. This is how we have to choose which VGS is coming. So, we have finalized the value of VGS. Once you get VGS, calculate ID, VGS, whatever the relation you got. Step 4, obtain output KVL. Output. If output KVL is there, then substitute ID and solve for VDS. Therefore, Q point is VDS comma ID. This is how we are going to obtain VDS and ID. That's calculating Q point. 6th point, zero drift drain current. Zero drift drain current. For example, VGS versus ID. Temperature 1, temperature 2, temperature 3. If all are passing through this, and this is called IDQ. If you can take that, such a voltage is called zero drift drain current. Zero drift drain current we are calling as abbreviation. What's the meaning here? The drift in the drain current is zero. When the drift is zero, if you take such a point as a Q point, it's going to be the most stable. That's why we call it as stability aspect. How to achieve stability in FETs? Okay. How to achieve this condition? First, we'll understand what are the reasons for this. Normally, whenever temperature change, current should change, but there's no change here. That means there are two anti-effects are coming. Two anti-effects. What are the two anti-effects here? Let me tell you. First one, as temperature increase, mobility increase, collisions occur. When collisions occur, what will happen? Amount of current is decreased. How much decreased? This is called 0.7% decrease. 0.7% means what? Change in ID is 0.007 ID. Call it as first equation. B. As temperature increase, junction voltage decrease. When the junction voltage decrease, junction width is decreased. When the junction width decrease, channel width automatically increase. When the channel width increase, what happens is ID increase. Therefore, in one aspect, ID is decreasing. In other aspect, ID is increasing. If these two quantities get equated, you will get a nice standard value. So that standard value, how does it come here? Change in VGS by is there. If you check change in ID is 1 by GM. Now what is change in ID? That means change in ID is equal to GM into VGS, and that is 2.3 millivolt into GM. Equate this, you call it as second equation. Now this is increasing, this is decreasing, this is increasing. Equate them. So 1 is equal to 2. Why 1 is equal to 2? Because both are same, change in ID. So 0.007 ID is equal to 2.3 into 10 power minus 3 into GM. ID by GM is equal to 0.314 will come. If you do that, that is nothing but 2.3 into 10 power minus 3 by 0.007. Then you already have one equation. ID by GM is equal to half of VP minus VGS. Therefore, if you equate these two, VP minus VGS is equal to 0.628. This is the condition for zero drift drain current or stable Q point. If you design a circuit for this, we are going to achieve the most stable point. Seventh point. Where to locate Q point? Just now in the previous topic, we have seen how to locate. How to locate is a procedure for locating Q point. Where to locate is a graphically to say where. For example, look at your characteristics here. VDS versus ID, and this is the characteristics you have. VGS1, VGS2, for example, and this is generally called constant current characteristics. In fact, this is a name that I am popularizing it. It's called constant current characteristics because the current is constant. Constant there. You have two aspects here. If it is JFET, we call it as pinch off. If it is mass, we call it as saturation region. Saturation. JFET, MOSFET. So when it is, therefore, whether it is pinch off or saturation, we will follow constant current characteristics. And as I've been telling, if you take DC load line, is a VDD here, and this is VDD by RD plus RS. Now generally, what is the best location to do? Center is the best one. You take the center of the DC load line so that you can get a maximum signal. We call it as signal handling capacity. How much it can handle. Now I'll just tell you what are the ways to say. So roughly this is VDD by 2. So the first requirement is locate Q point in constant current characteristics. What for? Only in this region it is acting as amplifier. Amplifier. VDS approximately VDD by 2 to have maximum signal. Approximately, there is nothing like that. So that you can have maximum voltage. Small ID less than or equal to capital ID. This is called small signal drain current. Small signal drain current. This is called zero signal drain current. Small signal drain current, zero signal. Small means AC. Zero means zero frequency, DC. So AC should be generally less than or equal to DC. You know why? Suppose you have this as a DC and signal, if it goes beyond, this portion is clipped off. That's why AC should be, this is AC. AC should be less than DC, always. This is another good thing to see how to really locate. Suppose you see this region, we call this region as breakdown region. Breakdown. So never choose Q point in breakdown. Never choose Q point in breakdown region. And the fifth one is, because if you take in the breakdown region, this cannot act as a amplifier. Then see that VDS is greater than VDS saturation, because the saturation is starting from here, or constant current variance is starting, so that it's not in the switching. This enters what you call constant current characteristics. So the value should be chosen such that you are not here, but in this region. That also half is better. For that, you know what happens? ID is approximately VDD by roughly ID plus RD plus RS. Why? Because half will go to transistor, half of that will be distributed among this. If you really look at this, how much is going to the output? Half. That remaining half is divided between two resistors. So this will be best thing to really talk. This is where and you locate the cue point. Requirements of a biasing circuit. What is required of a biasing circuit? Step 1. First point. Single battery to bias both input and output. Why single battery for both? Because if we use one for input and one for output, it will become bad. So we have to go for single, that is to decrease cost. If you use one battery for both, that is very cheap. Negative feedback for DC. What for? To stabilize cue point. How to stabilize cue point? Third one. No feedback for AC to avoid loss of gain. Loss of AC gain. Because whenever you give a feedback, there will be loss of gain. That should be reduced to avoid loss of AC gain. Fourth one. Potential divider at input. What for? To vary cue point. Then you ask me, why should we vary cue point and then stabilize? Are they not contradicting? They are not contradicting. At every varied value of cue point, it must be stable. Because I need to vary the cue point. For example, look at your characteristics. VDS versus ID. For example, if you take your DC load line here, if you take cue point here, you will have small signal. If you take cue point here, you will have large signal. Small signal will handle small cue point, less cue point will handle small signal, more cue point will handle large signal. So to handle different signals, cue point has to be large. Therefore, it has to vary. How to vary? Potential divider at the input. These are the 4 requirements. If these 4 requirements are met, we call it as biasing, best bias.